Hi, in this video we'll go through two questions on electrical potential. That will be 10.5 and 10.6. So now please pause the video, try yourself.
A few moments later.
Okay, to me this question is a bit disappointing because when I look at the picture, I thought it's something to do with circular motion, but it actually doesn't. So it's just simply asking you electrical potential, and they have given you the distance, so I'll put an R here because that is something we are going to substitute into the equation later. This is a charge. In fact, they shouldn't tell you because this is a proton, right? One single proton, and one single proton will have the same magnitude of charge, because you should know that for electron, for one electron, that will be 1.6 times 10 to the power of -19 C. That is an elementary charge in Coulomb. You can find in the data booklet. So remember, for proton, it is going to be the same. Right? If you have only one proton, it's just change the negative into positive. So maybe in the IB exam, they may not tell you this, and you have to be smart enough to recall that. So for part A, it's just simply recalling the equation for electric potential. So the symbol you should use is VE, and the equation you can find in the data booklet if you don't remember. So you've got K, the Coulomb constant, Q is simply the proton charge, and also R. So you should be able to substitute and find out the answer. I'm not going to do it. So for part B, they are asking you to calculate electrical potential energy. So just like in gravitational potential and gravitational potential energy, the difference is what? It's only missing the mass of that particular object. So when we put the context into electric, then it will become charge. So obviously, even if you don't have to go back to look at the data booklet, you should know that the energy should equal to K, Q, well, Q of each of them, say Q1, Q2 if you like to say. And then, well, the radius is still the same. And so that's pretty much it. So you just have to get the answer from part A and multiply the elementary charge again, and that will be your answer. Okay, so these will be the answers after you substitute into the calculator. Check it yourself. Okay, next question. Make sure you finish it first, right? If you haven't, you can still pause the video now. Alright, for this question, is again asking you electric potential. So the equation that you should consider is KQ over R. So R is the distance from the test charge. So for example, now they are talking about the distance X. So imagine there is a test small positive point charge here. Okay, and you are trying to look at is electric potential at this point due to the charge on the left hand side and also due to the charge on the right hand side. So each of these should contribute into the final electric potential. So that is to say, the expression, if I have to make it better, then it should be K big Q over X plus, because when you do electric potential, you have to recall that it is a scalar. So it's different from, for example, field strength. If you recall what you learned, field strength is a vector. And for electric potential, you may want to remind yourself that this is a scalar. And so for scalar, they are friendly. Okay, this is a word that I make up. You don't have to worry about what direction they are because they don't have direction. So what you do, simply, you just add them up together. Okay, and for field strength, for vector, you then have to think about what direction and maybe taking sine, cosine, or at least doing plus or minus if they are in a different direction. Okay, so for here, you just have to do K big Q over X. And then for the other part, on the right hand side, it will be also K small q. And in fact, these both are positive. So that's why there's no negative here, because the plus is like hidden already. Over this distance, so it's a bit tricky because they didn't give you a notation. So let us just name one. Let's just call it R then. Then that will become R minus X in this case for a distance from the test charge to the right hand side, that one. Okay, so this is the mathematical expression. However, I think even if you don't put down this, you should be able to know that, because when you look at this expression, when the charge is bigger, then the value of the electric potential is also bigger. And when you are closer at the very beginning, from near to zero, that means the test charge is also near on the left hand side. So the big Q, that charge is going to give you a more significant effect. And therefore, when you compare left and right, B should be the correct answer, because you can look at left hand side and right hand side. This will give you a greater value, right? While on the right hand side is rather less. So B is a correct answer here.
Here comes a new challenger.
Bonus question. So if you haven't tried this bonus question yet, you may want to try it now because it's quite interesting. So as you know, A, C, and D options are wrong just now because they don't match with the diagram. So my question is, what picture, like what configuration of those charts, if you can manipulate those charts, like increase, changing it, doing whatever you like, how can you change them so that it can match with A, C, and D respectively? Think about all cases.
A few moments later.
Alright, so here will be the answer. For A, you can see is very symmetrical, and you don't see any difference like in terms of magnitude. They kind of, it's just really symmetrical. And so obviously what happened is you have a charge of, say, Q, and correspondingly here you also have a charge positive Q, and they are the same magnitude. Alright, so basically that's what you have for option A. Option C is like the reverse of B, because you can see this side is a bit greater than the left hand side. So so you just have to reverse the question from left to right or the other way around. So the big Q is of a greater quantity of charge, obviously, will be on the right hand side, while the left hand side will be less charge. Lastly, for D, the answer is actually impossible. Alright, because the main issue is you can see in the middle it hit 0. So think about this. For the equation, that's why I actually plan to write down the equation at a very early stage. You can see that this term, no matter, assuming there are two charges, obviously. So this is positive, this is also positive, and you're adding them together, and there's no way you can get it to be 0, because positive per positive is positive, right? And they are non-zero anyway. So you can't get them to be 0 in the middle. The only case where you may get an electric potential versus distance, this kind of graph, and having 0 is when you have a positive charge and maybe a negative charge, and then in somewhere in the middle, if they are of the same charge, of course, then in the middle, exact middle, then they will hit 0. But then the problem is when you get close to this negative charge, then think about the equation. It will become negative kq over like something, right? The distance that you, depending on how you set up. But the most important thing is negative. And so in this case, the graph will more become like, oh yeah, it does actually hit 0 at a certain point, but then maybe it will become something like this instead. Okay, so that's not something we have in D. And again, this graph is really impossible. If you can think of any situation that would really generate this graph, let me know in the comment section below.